Okay, because you are the graduate students, right? So maybe in the future, very near future, you may have to do the research by yourself, and maybe you have to publish your own paper. So I will also in this because I have told you that because these subjects I will teach for my lab students, and after finish this course, my lab student can write their own papers. So in this class as well, I will always show you the papers and then try to make you understand about how to read the paper, how to understand how to develop the research by yourself, right? So maybe you have known that this part is, we can call it the abstract part, right? We show the summary. I cannot say summary. We will say, in this part we will say what, why, and how, right? What, why, and how of this paper. For example, what is paper about? And then why do we have to do this paper or this research? And then how can we come up with this research? Okay, and then we go to the part that is the introduction, that we will make some or show you some history of the Ball curve and Bezier curve, right? And in this paper we use Hermit 2 points, right? Maybe you are, after you finish maybe 4 weeks already, right? In CAGD you can read this paper. Go back to 1990, right? You can understand this very easy, right? Starting from Bezier, right? You have already known about Bezier, and Burnside polynomial, right? Can approximate. Okay, maybe it's a good idea that you can read this paper in order to confirm your idea or your notion about CAGD or computer-aided geometric design. Okay, Bezier uses Burnside polynomial as basic function in this scheme, right? Okay, then I will go quickly through it. Okay, and the second part on this paper will show you about the hello, what's happened? I lost my connection, right? Hello. Okay, I come back. But the thing is that I have to share screen again. Okay. I lost here, right? Okay. I've talked about the cubic Ball curve, right? We have the highest degree of Ball curve. That is 3, right? And there are 4 control points, right? The index is the index are 0, 1, 2, 3, right? And you can see that for cubic Ball curve, right? B3T, right? T stand for the degree, right? I from 0 to 3, Vi, vertex I, right? Multiplied by beta I, right? This is a cubic Ball curve. And then, okay, they shown that this curve can approximate the control point formed by joining the point together. And then it is the affine combination because all beta I t is greater than or equal to 0. And it is affine combination. It is convex combination and it's affine combination because the summation of the polynomials is sum to 1. Right? Can be sum to 1. Okay, and this one is an example of cubic Ball curve corresponding to the control point. Okay, and then Professor Sai tried to generalize because there is only one model for Ball curve, that is a cubic Ball curve, right? If you want to get the quadratic curve, what does it mean by quadratic curve? Quadratic ball curve means the curve of degree 2. You can do by combine these two, beta 1t and beta 2t. You can plus them, right? And you can come up with the polynomial in between. Okay, we can start from b0, 1 minus t raised to the power 2, and beta 3t is equal to t square. Okay? I think maybe I will have to use my iPad in order to you can follow. Okay, during I'm waiting for my Hello, I'm back. Can you hear me? Okay. Okay, I will. Because we have start from the cubic ball curve, right? So I've just told you that if we want to, what's happened? Okay, this is a cubic ball polynomial, right? This one, there are four polynomials, but if you want to make it to be quadratic curve, right, of ball, okay, you have to start from this one is beta 0. This one is beta, maybe you have to change it to beta 2, right, in order to make it to be quadratic. And then if you want to get, because this polynomial, these four polynomials you sum to 1, right? So beta 2, no, beta 1 t will be 2t1 minus t square plus 2t square 1 minus t. Okay, this will sum to 1. Am I right? Am I right? Because of this formula, right? And this one is going to be the first polynomial. This one is going to be the last polynomial. So the less which should be okay. I want to indicate that it is the degree 2, right? B21, okay, will be equal to B31T plus beta of degree 3 index 2. Okay, so we can have 2t 1 minus t. This one is a common. We try to take the common variable here, and then when we get this, the first term you have 1 minus t and plus t, right? This one is an expansion form. Okay, so we can group into this form, right? And this one will can be eliminated because it is 1. 1 minus t plus t is 1. So beta 21t will be equal to 2t1 minus t. This is the polynomials, the second polynomials of quadratic ball curve. And the idea comes like this, because the generalization of the Sidebar curve will do the same thing like this. So okay, I'm not sure whether you have finished this or not. Okay, you can write. Okay, I help you finish all. Finish writing. So this is the idea that Said did for forming the generalization of ball curve of any degree. Okay. So this one is the generalization. An explicit representation of Hermite two-point Taylor. Okay, we are not going to go into the detail of the proof here, but I want to show you about the result of generalized basis function. Okay, the idea of the forming generalization for the base cubic for the ball curve of any degree, starting from the Hermite interpolation, right? And then we can come up with the generalized ball curve of odd degree. Of odd degree. Of odd degree, right? So the formula for the odd degree is very simple, right? You have to write it in terms of m, right? M is the middle point or median, right? B 2m plus 1, okay, will be the index for the Ball polynomial, generalized Ball polynomial. Okay, and okay, so we can have the Ball polynomial of odd degree, right? The formation will be like this. The polynomial is here. Okay, so here we are the set of the Ball polynomial. Okay, and if you want to find if you want to find the Ball polynomial of even degree, you may have to do the same thing as I've just told you, that you can get the two middle polynomials. For example, if you want to get 2m, right? If it is so you have to get m and m, you have to plus to add polynomial of degree of index m and m plus 1. Okay, you can get the even degree, and then you can also get the recursive algorithm for Sidebar. Like this is a way of construct the Bezier curve, right? You can use 1 minus t, 1 minus t, right? You can do the linear interpolation. This is for the Bezier curve. And for the Wang-Ball curve will be different. Okay, these are the proof. I'm not going into detail because this course is not about to teach you about this paper. So I will just want you to see the overall of this paper in 1989. Okay, so in this paper we have the recursive formula for the Sidebar curve. By that time we didn't call it Sidebar curve, we just call it generalized Ball curve. Okay, so in order to print out or in order to calculate for the points on the curve, right, the algorithm requires that the generalized Ball form of degree 2m plus 1, right, this is general degree of n, will be reduced to Bezier form of degree m plus 1. And then we can use the Recursive algorithm in order to print out the first half and the second half of the Ball curve. So I can say that in order to calculate for the points on the Ball curve, you have to calculate only half of Ball curve, and only half of Ball curve can be reduced into the Bezier curve of the form of degree m plus 1. Okay, that's quite complicated things. Okay, so this is go back. I bring you back to the 1989. Okay, and okay, we have, and this is 1991. Said and Goodman try to develop the properties of generalized Ball curve and surface. Okay, and here is it is the, if you could remember degree elevation and degree reduction, right? In this paper, it will show you the degree elevation for this one is for Bezier curve, right? But if you want to find the degree elevation for Sidebar curve, right, you may have to use this to employ Bezier curve degree elevation in order to calculate for the Sidebar curve degree elevation. degree elevation. Univariate generalized ball basis will be like this, right? This is the in the form of the odd degree. And you can see odd degree. See, the function is only for odd degree. What's happened? I'm trying to clear this. Oh. Okay. What I'm trying to tell you is that if you can see the paper in the past, right? If you want to, if you want to generate the ball curve, generalized ball curve, okay, you may have to take some time in order to understand about the equation, especially if the generalized ball can be written in terms of odd and even degree. This is quite difficult to understand. And also, but if you can combine them into just only one formula, right? And use n as any degree, right? It can make your life easier, right? Like last time that I asked you to write the polynomial for the Sidebar curve, right? It's pretty easy if I combine them into the mathematical formulas, and then there are just only 3 or 4 lines of code, and then you can write it, and that's all. You can calculate for the curve very easy, right? And when we go to the property of the curve, right? For example, the degree elevation. In this example, you are considering the degree elevation for general ball curve, right? Okay, this one is the formula, right? This is the way that to represent in the visualization representation of the degree elevation from degree 7 to 9. So you can see that for the Bayesian, for the generalized ball curve, if you want to raise the degree, right, it has to be raised from one odd to another odd number, right? 7 to 9, 9 to 11 or something, right? So that is not make sense. Okay, so this one is to lower degree, right? From 7 to 5, right? It can be also, we can also use the formula like this. Okay, if we have the simpler algorithm in order to convert to do the degree elevation of any curve, that would be very good, right? Okay, this all for this paper. I'm sorry, I don't have the paper for Wang, right, in Chinese. Okay, but I have Wu, right? So in Wu, right, this is what we are going to talk today. This is about this paper, 1996, right? If you could remember, In U, right, Sideball, we separate ball curve into two kinds, Sideball and Wang-Ball. We put Side and put Wang before ball because ball is more important. The most important name will be closer to the curve or to the noun, okay? But less important will be put in front of it in order to maybe to model the letter or the following, right? So this will call Sideball curve, right? Can be written in terms of the, okay, to put in the ball polynomial of odd degree. You can see this one is odd degree and even degree. Okay, so but if you come back to my lecture note, to my PowerPoint, you can see that I combine odd degree and even degree already, right? So I make your life easier. Okay, but I want to show you that before we can come up with that formula, right? We have, okay, and here is the degree elevation and reduction. If I ask you to write a program in order to find the degree reduction, degree elevation for Sideball, you can use this formula. But you can see that it is difficult to guess what does it mean by this, right? So we cannot check for the correctness of this paper, okay? Not only for the degree elevation, but also for the degree reduction as well, okay? But we can do this one, degree recursive algorithm. As I've just told you that in 1989, right? In that paper, they said that in order to calculate for the Sideball curve, right, you have to reduce the nth ball form into Bayesian form, right, and then use the Castro algorithm in order to compute the points for the half form of the Bayesian curve, right? This one is the first recursive algorithm for Sideball, right? But this paper presents a new recursive algorithm, right, for the Sideball curve, right? You have to separate into odd numbers, and then have to guess this, and then you have to follow these 3 steps in order to come up with the result. Okay, that would be to calculate for the points on the Sideball. Okay, this I will leave you to try to solve this problem. And this one is a linear interpolation form of Sideball. Okay, if you want to understand about this recursive algorithm, you can also understand about this formula, this form. Okay. And also for Wang-Ball, right? Wang-Ball, we have to split into even and odd degree as well. And then they provide, this paper provide the degree elevation for Wang-Ball as well. But this one is clearer, okay? You can understand it. And it is also provide the recursive form of this. What I'm trying to say is that it is in this paper, this paper provide many things about the properties of Wang-Ball curve and Sideball curve, but because it is all document, so you can see that it is not clear in some formula. So it is, I can say that it's not clean. Okay, so Okay, so that's why I reformat them and try to make it easier to understand. Like this, right? I start from, okay, in order to represent the Sideball curve, right, I represent it in terms of S, right, instead of beta, and then S and I, right? I don't have to separate into two cases, odd and even cases. I can just simply use n, and n will refer to any number n, right? So I can come up with the generalized ball curve. This formula can be done. This formula could be done by using polar form approach. In, I'm not sure, 1992 or something by Ramshaw or by Tang Wan-Ter. He's a Vietnamese PhD student by that time, right, in AAT. And after we use that polar form approach, we can come up with the very nice formula for this Sideball curve. And Sideball curve will be was cleaned up by Hong Li Tien. This is also the Vietnamese PhD student as well, right? Before we can come up with this form. I didn't develop this form, okay? And then when we come up with this one, okay, we are thinking about the recursive formula of Sideball. If you remember, I've just opened the paper 1996, right? And the recursive formula for Sideball is very long, right? We have 3 steps, and then we have to guess about the formula as well. But if you see this formula is quite clean and well defined, right? I developed this formula with my PhD student, and I also provide the proof for this equation as well. Okay, so it will be easier to use this recursive formula, which is like the Cassel algorithm for Sideball curve. And when we can develop this one, we can have the geometric linear interpolation of a Sideball curve. That is very easy to look and to check for the correctness of this curve, right? Actually, Sideball curve, if you want to get the point on the Sideball curve, like this one, we have the degree 7 of this curve. And then if you want to calculate Sideball point on the curve, right, to get P70, you can use this geometric interpolation of Sideball curve, right? Okay, and this form is exactly the same as this one. Okay, and this one is a triangular scheme of, or sometimes we can call bubble scheme, right? This one is a linear interpolation of the points from the given point. In this case, this is an even case. This one is odd case, like 7. Right? You can come up with P70, which is a point on the curve. And you can use this. And this one is another representation of this one, and this one also, right? And I've just told you that the polar form for Sideball had been proved before, right? In order to get the result for you can see that this one is floor function n divided by 2 plus I and I, right? If you are familiar with this form, and then I come back to this, okay, you can see that the coefficient is similar, not similar, it's the same, right? Floor n divided by 2 plus I and I, right? This is binomial. Okay, you can see that the coefficient are the same, because this is the polar form for a Sideball curve. In the past, when I taught this course CAGD, right, I have one chapter that is very difficult to understand and very slow to explain to my students as well. But after I can finish prove something, right, like monomial form, right, I'm going to eliminate this part from my course, right, because it's quite difficult to understand and you don't have to do this, right, because you have to know how to convert from this form, polar form, into this form, right, and this quite tedious and no one would like to do this, right, because we have the monomial form which is better and easier to understand and we can apply to any kinds of property of the curve, right? For example, okay, this is a linear interpolation matrix, right? I will show you later in the work by Delgado and Peña, Spanish researchers, right? They try to develop another kind of curve, right, and use this matrix interpolation. Sometimes this linear interpolation matrix will show us the interpolation between the how can I say, the basic foundation of the curve. Okay, I will talk about this later. And this one is a monomial. This is the this very useful, right? We can use monomial in order to find the degree elevation. We can use monomial form in order to find the degree reduction. We can also use monomial form in order to convert from one basis to another basis that I'm going to talk to you later. Okay, and this one is very important, monomial form, right? And this one also, I have a paper that prove the correctness of this formula. I want to convert from, I have to convert from the side generalized ball polynomials into monomial form, right? This is the generalized monomial form of Sidebar curve. Okay, up to this, do you have any questions before we go to Wang-Ball? The reason why we have to use Sidebar curve because in the past, if you want to draw a curve, you have to use only Bezier curve. But Bezier curve, you know that the complexity, the time complexity computations will be big O n square. That is very, very high. Okay, it's still not acceptable. So, but when we talk about Sidebar curve, right? Sidebar curve is more or less is its algorithm is recursive algorithm is faster, a bit faster than Bezier curve. So that there was an idea that if we could convert from Bezier to Sidebar curve, and then okay, if you want to draw a Bezier curve, but if you convert Bezier curve into Sidebar curve first and then use recursive formula for Sidebar, right, to print out to draw the Bezier curve, that will be faster. Okay, that was the idea by that time, right? But after that, in 1996, right, Wang-Ball curve was claimed to be big O(n) algorithm, big O(n) recursive algorithm, right? So instead of convert from Bezier to Sidebar, we can convert Bezier to Wang-Ball in order to compute Bezier curve faster. So Wang-Ball curve will be more important and more popular than Sidebar curve. Okay, so that's why we have to know these two generalized ball curve, right? Sidebar and Wang-Ball. And Wang-Ball, right? Like last time, I have already shown you about this form, right? And we also have written the code, the Mathematica code already. Okay, and also the same thing as the Wang-Ball curve, right? As a Sidebar curve, we also have the Wang algorithm. Okay, this is the Wang algorithm, right? That was shown in the paper in 1996. I could catch up this formula because the manuscript is clear, so I can come up with this one. And but the side recursive form of side algorithm, it was written similar way like this, right? The item 1, step 2, and step 3, right? And we have to perform like this. This is the Wang algorithm, but we don't like this form. This form is difficult to implement, so we use, okay, the Wang algorithm require 3n-1 divided by 2 additions and 3n-1 multiplication. So you can see from this formula, right? This is big O n, right? This is for n odd or n even. So the time complexity for computing a curve using Wang algorithm will be big O n. Big O n. So there was an idea that if we can convert, if we want to show Bezier curve, right? Draw Bezier curve, right? In order to draw Bezier curve, we can transform or convert into Wang form. What does it mean by Wang form? We will create the same curve but using different algorithm. Instead of using the classical algorithm in order to compute the point on the Bezier curve, we can convert this into new control point of Wang, but still we have the same Bezier curve, and then we can use Wang algorithm like this. Wang algorithm in order to generate the curve. This curve will be the same, exactly the same as Bezier curve. And this one is big O n. But I'm going to address here that this direction transform, the big O for transform is big O n square. When you say that, oh, this is not square, cubic n 3, big O n 3. You can have an argument that, oh, this one is big O n raised to the power 3. That is not acceptable, right? So the overall of the computation will be big O n raised to the power 3 plus big O n, right? But what I'm going to say is that in order to compute a point on Bezier curve, if you want to make a smooth curve, maybe you may have to calculate for 500 points. Okay, in order to get the smooth curve. But you can just simply transform this only one time. Once. This one will do once. But this one you will perform 100 or 500 times. 500 times. So it is not significant. This term is not significant. This one is more important. Okay, do you understand my point? So in the year 2000, my publication with my advisor when I was doing my PhD was published, right? We suggest the way to print out, to draw the Bezier curve by converting from Bezier curve into Wang-Ball curve or Wang-Ball form, right? And then we can use Wang algorithm in order to calculate for the points on the curve. So that's why Wang algorithm or Wang-Ball curve came to be popular, very popular, because of its linear time computation. Linear. Okay, I also provide the things that is similar to Sidebar curve, right? For example, like recursive formula for Wang-Ball curve, right? This is very short, right? Comparing to this one. This one, which one do you prefer to write the program? Which one do you prefer? You prefer this one, right? This one is shorter, easier, and cleaner. And this one is, oh, wow, it is confusing, right? Am I right? Please don't say that because I'm your teacher. So when I say something, it should be correct. Maybe you can have the argument to me as well. Okay? But it is obvious that this form is very difficult. Maybe I can ask you to try to write the program Wang algorithm. Okay, and this one is a geometric interpolation of a Wang-Ball curve. And this one is triangular scheme. Okay, it can be, this one is easier. For Wang-Ball curve, why the interpolation is very fast, right? Because for degree 6, we will interpolate only 2 times. In degree 5, which is odd, we interpolate only 1 time, and 2 times, and 1 time, and then 2 times, and then 1 time. So this is the way that Wang-Ball does. So that's why it is very fast, right? Because the calculation will be 1, 2, 1, 2, 1, 2, right? And it is 1, 2 plus 1 plus 2 plus 1 plus 2, right? So you can see that it is the multiplication of 3, right? It is a constant. It will come to linear. Okay, this is for odd degree, right? You will interpret just 1 time. How about the others? The other you just simply copy into the new control point. And then 2, 1, 2, and 1, 2, and 1. Okay. So the calculation for the, okay, algorithm will require 3n minus 1 divided by 2. Okay, that's what I've told you. That is a multiplication, multiplicity of 3. 3n minus 1 or 3n, right? Multiplicity of 3. Okay, and this is the polar form for Wang-Ball, right? In order to get the very clean and nice formula, right, we can just simply use the polar form approach in order to come up with the nice formula, right? And this one is also the linear interpolation of matrix, in linear interpolation matrix of Wang-Ball curve, right? Very simple, right? 1 minus t, and this one we have 1 minus t, 1 minus t twice. And this one will be 1 minus t and t 1 time. This 2 time, 1 time, 2 time, 1 time. Okay. Okay, here is the monomial matrix form for Wang-Ball curve. There are only four lines of code. Very easy. Okay, so we are finished for the Sidebar and Wang-Ball curve. The next topic that I'm going to talk is about how to convert. Because I've just told you that if you can convert from basic Bezier curve to Wang-Ball, you will have the benefits for conversion. But how can we get that conversion? Okay, that's we are going to talk about this in the next presentation.